Let's look at how to graph the tangent and cotangent functions. I'm going to start with tangent, y equals tangent x. We're going to rely on a lot of the skills that we had for sine and cosine, but we do need to know what the basic graphs of tangent and cotangent look like. So the first thing to note is there is a major difference, which is that the period of both the tangent and the cotangent is only pi in comparison to sine cosine, which is 2 pi. Another big difference is that tangent and cotangent do not have infinite domains. Their domains are not negative infinity to infinity like they were with sine. So we're going to talk about where those breakdowns occur. Tangent, we know the values from our unit circle special triangles. We know one of our values is 0, 0. We also know that we get a nice even 1, y value of 1 at pi over 4. We also know that tangent is an odd function, so that means we'd have to get a negative 1 at negative pi over 4. So those give me a couple nice pretty values to work with, kind of the same way we did for sine cosine. And then we have another known, which is that the pi over 2's, negative pi over 2 and pi over 2, we have that tangent is undefined. We can't find the tangent at those values. And if we think about why that is the case, well, tangent is that ratio of y to x. And so if we think about our unit circle, this is our unit circle, 0, pi over 2, 3, the pi, 3 pi over 2. As we get really close to the pi over 2 up here, the y's become really, really close to 1, and the x's get really, really small until eventually the x's are 0, meaning that we can't divide by that 0. But if we think about the progress up until that point, right? If we're looking at, when x is 1/2, we'd multiply by the 2, and the y would be getting close to 1, not quite to 1. But then if we look at 1/3, the y is even closer to 1, and the x now we'd be multiplying by 3 because we have to do the reciprocal. If we were to look at 1/10, now we're really close to the 1 that we expect at pi over 2, but we'd have to multiply by 10. So what we can see is as we get closer and closer to this y-axis, or the pi over 2, our x values are getting really, really close to 0, making the fraction as a whole go to infinity, meaning that we have an asymptote at pi over 2. Negative pi over 2 is the exact same story, except for the fact that we are going to the negative direction, meaning we are going to a negative infinity, where we have an asymptote going down, where our graph is approaching in downwards direction. So let me attempt to draw that a little bit more smoothly. It looks almost like the x cubed function. It is not. It is different for the obvious reason it's not the same function. It's tangent, it's a trig function. But there's obviously some different points along the graph, but the biggest difference is the fact that it does repeat. It is a wave. And so if I wanted to continue drawing waves, I could do that. If I were to go out to 3 pi over 2, we'd see that we have another asymptote. We'd see that we have another tangent graph, and then if we were to keep going, we'd see more and more and more, right? I'm not going to draw all of those, kind of like I did with the sine cosine. I'm only going to concentrate on one wave or maybe two, but I'm going to concentrate on the one centered around 0 at first. That will be a little bit easier. Let's go ahead and talk about cotangent before we start applying all those transformations like we did with the sine cosine. So down here I'm going to do y equals cotangent x. And I'm actually going to use my graph of tangent to help inform me of what this should look like. Well, I know cotangent is just the reciprocal for tangent. So if I had 0 before, well, that's going to be a problem. That's going to become an undefined value. So I have now an asymptote on my y-axis. We're going to be shooting to one of the infinities. However, the old asymptotes, those are actually going to become values that go to 0, because if we take the reciprocal of something that's going to infinity, infinity over something is going to be, when we take its reciprocal, something over infinity, that goes to 0, if we were to look at some limits. So those become x-intercepts. If we're to take the reciprocals of these 1's, the reciprocal of 1 is just 1, and the reciprocal of negative 1 is just negative 1. So those actually don't change, those points right there. At pi over 4, I have a 1. And at negative pi over 4 over here, I have a -1. Now, the problem is I'm ending up with, half of a wave on each side. So I have a piece that looks like that. We know we are going off to our infinity. I have a piece that looks like this going down to our negative infinity. Not a great drawing. I'd really like to see what the continuous wave looks like. Well, remember that these cotangents, this is a full period, so they're going to continue to repeat. So if I were to extend it out this way by another pi over 2, meaning I'm ending up at pi, that will complete my wave, and I'll have a piece that looks like that. And again, these things continue, so we just continue to see this pattern over and over again. So let me draw the cotangent function right under the tangent here, but I'm going to draw it a little bit cleaner now that we've talked through it. So if I want to draw one period of the cotangent function, I'm going to start at 0. I'm going to realize that, hey, this is an asymptote. I'm going to go over to pi. That's another asymptote. Halfway in the middle at pi over 2. That is going to be our x-intercept. Cotangent is a decreasing function, so it's going to actually start at 1 at the pi over 4 and go down to the -1 at 3 pi over 4. And so if I label those pi over 4 and 3 pi over 4, then I'm going to be able to see my full graph. There, that's going up, and then that's going down. So it's a decreasing function. Again, kind of looks like that x cubed, but it is going the wrong way around. Now, all those transformations that we talked about with sine and cosine, they're still true. So if I write out the equation y is equal to a tangent bx plus c plus d, the a still relates to an idea of amplitude, but the thing to notice here is we don't have amplitude. Amplitude was the highest or the low that we reach. We go to infinity. So the a, if we're going to discuss the a, we have to go back to calling it the vertical stretch by a, or remember it can be a compression too, depending on if it's being multiplied or divided. So we're going to vertically stretch or compress by a. The b does affect the period, but what the b now does for us is it allows us to find the period by taking pi over the b, and we're using the absolute values of these things. The negatives come into play with reflections. Because the base period of tangent is only pi, we have to divide pi by b, not the 2 pi like we were doing for sine and cosine. The c still relates to a phase shift. That phase shift terminology has not changed. The phase shift will be a negative c over b, the same exact as it was for sine and cosine. That doesn't change one bit. And the vertical shift is going to be exactly the same. We're going to have a vertical shift given to us by the d by d either up or down. Now I called this one tangent, but it would work the exact same as if I'd said, hey, this is cotangent. They're going to play out the same. Remember, a negative in front of the function up here would give us a reflection about the x-axis, and if we were to instead have put the negative on the b, that would be a reflection about the y-axis. So let's take an example. Let's say we have y is equal to 2 tangent of 3x minus pi. Well, I'm going to just take it piece by piece, the 2. I can't call it a amplitude anymore, but I can call it a vertical stretch. By 2. The period is going to be influenced by that 3 there. The period will be equal to pi over the b, which is pi over 3, and that doesn't clean up at all. And then the phase shift is still the negative c, or negative pi turns into a positive pi, over the b, which is 3. And so we've kind of lucked into the phase shift giving us exactly the period. Makes it a little bit easier to graph. So let's see how that'll work. We do have tangent, so tangent typically starts at the 0. Let's go ahead and treat it as if it has that phase shift. So we'd say, hey, we have to come over here to the right by pi over 3. And it is to the right because we use the opposite sign. I know that this is my new 0. My period of pi over 3 tells me that actually if I just started at where it typically starts, that would give me the same wave. Those two will be the same wave. I do want to figure out where those asymptotes kind of to send the ends off to the infinities, and so the way I'm going to do that is a little bit different than I was doing with sine and cosine. I'm not just going to go from the starting point to the ending point. I want to see that continuous wave between the two asymptotes. So I'm going to take my period and divide it by 2. Well, pi over 3 divided by 2 is pi over 6. So that means if I go pi over 6 units any which way from the 0, I'm going to run into an asymptote. So if I were to come off the pi over 3 at pi over 6, there would be an asymptote. If I were to go over pi over 6 from pi over 3, we need a common denominator. That will be 2 pi over 3 plus 2 pi over 6, excuse me, plus pi over 6 would give me pi over 2. That would be another asymptote. Or I could have, if I had used the 0, I could have used a negative pi over 6. And that would be my asymptote passing through that negative pi over 6. Then I'm going to continue to kind of quarter this thing up. So if I look at the nice even ones where they occur, it's no longer 1, it's going to be equal to 2 because that was our vertical stretch. So my even numbers, or my nice clean values, will be at 2 and negative 2. The halfway point, so I need to figure out what those would be. Well, this will be pi over 12. Half of pi over 6 is pi over 12. This one would be a negative pi over 12. And with a tangent, we don't have any sort of reflection, so we expect that to be increasing. It will be our first point, or I shouldn't say the first point, but our clean point will be down there, and the other one will be up here, and be pointing down, be pointing up. That's, of course, me shifting it back to origin because it happened to so nicely align. If I'd done it over here, I would have just needed to find those halfway points, and whatever those values are, I do need to calculate those. That would be my graph, so I'd have to calculate this point and this point. Let's do one with cotangent. Let's take y is equal to, let's do a fifth cotangent of x over 2 plus pi over 3. So again, we have an a, b, and a c. Let's define the vertical stretch or compression first. We do have a vertical compression in this case because we have that a value being less than 1. Vertical compression by a factor of 5, meaning we're fifthing this thing. We have a vertical compression. We have a period adjustment. Our period is now going to be the pi divided by the 1/2, and pi divided by 1/2 is going to give me 2 pi. Then our phase shift will be equal to the negative c, or negative pi over 3 divided by the 1/2. And so if we divide by the 1/2, we multiply by the reciprocal, that'd be a negative pi, 2 pi over 3. And so let's sketch this out. Next, I'm showing a little bit more of my negative x-axis this time because I do have that negative phase shift. So if we think about cotangent, cotangent usually starts on the y-axis with a asymptote. It is always easiest to move the thing that is sitting on the y-axis. I'm going to shift that to the left by negative 2 pi over 3. That's going to be my new initial asymptote. From there, I need to move by a full period to get to the next asymptote. A little different than how I did the tangent. Because I want to see that full wave, I split the tangent up. I split its period in half to see where I need to get to each of those asymptotes. With the cotangent, because we started an asymptote, I'm just going to add the period to get to the next asymptote. So if I take 2 pi and add that to my starting point, well, I need a common denominator. 2 pi would be 6 pi over 3, and if I take away 2 pi from that, that would be 4 pi over 3. So again, I want to have these things approximately proportionally correct. This distance here should be approximately double this distance, so hopefully I've done a pretty good job of that. That would be my asymptote. Clean that up a little bit. So now I have my two asymptotes. I'm going to start looking for the other points. I know exactly halfway in the middle will be my 0. So if I add negative 2 pi over 3 and 4 pi over 3, that is 2 pi over 3. And then cutting in half would give me pi over 3. So that right there will be my halfway point. That will be my 0. Then if I look at my next halfway points, I will have, we'll start with this side. Negative 2 pi over 3 plus pi over 3 will be negative pi over 3. If I cut that in half, that would be a negative pi over 6. That will be my nice clean value, one of my nice clean values. And then the pi over 3 plus 4 pi over 3 would be 5 pi over 3. Cut that in half, 5 pi over 6. So just like with sine and cosine, we want to be comfortable with working with our fractions. We did have a cotangent, which means it should be decreasing, meaning we'll start out at the higher value, then go to the lower value, and we need to know what those values are. That was driven by my vertical compression of 1/5. So can't call an amplitude. It's not a highest point, but it is that nice clean value that we get on our y-axis. So the 1/5 up top, negative 1/5 at the bottom. So now I'm just going to connect my dots, approach my asymptote, miss my mark, but hit your marks, and then going down, we would get that. So hopefully you guys can do a little better on paper than I can on this computer screen. It's a little sticky. But it should have the general curve. It should not look like a straight line path, and we need to have those key points indicated. So with sine and cosine, we have 5 key points. With tangent and cotangent, we have 5 key elements. We have a pair of asymptotes, and then we have our 3 key points in the middle.